This lecture is going to go over some fundamental concepts of light and matter. So we're going to start off just reviewing. So far we've talked about some periodic trends, and we said the keys, we talked about atomic size. As we move down a group, the size of the atom increases. And as we move from left to right across the period, the size of the atom decreases. So in large part, these trends are due to the arrangement of electrons. And we'll understand why. But first, before we do that, we really have to understand a little bit more about the nature of electrons. And before we can understand the electron, we have to take a little detour and understand some physics, and first understand a little bit more about the nature of light. And so if we back up and go back through time a little bit, by the end of the 19th century, it's pretty well understood that light, right, visible light that we see, is part of a larger thing called the electromagnetic spectrum. And the electromagnetic spectrum is made up of a bunch of different things. And you can see a picture of it here. So things like gamma rays, X-rays, ultraviolet, infrared, microwave. We can see a tiny portion of it is visible light. So we can only see on our eyes this visible region of this spectrum. And all these things turn out to be various forms of light. And we can see all the different types of technologies and devices that utilize this spectrum. And the only difference between, red light versus an X-ray versus a microwave versus an AM radio wave is we can see here in the wavelength of this light. So it's all the same stuff. It's just different wavelengths of light, as we'll see. So a little bit more about waves. When we think about a wave, we have to sort of just understand some basics of wave physics. And so what we have here is a bunch of different waves. So here's a wave, and here's another wave, and then some others. A couple definitions that we should know. Amplitude of a wave, that's just the height of the wave. So on this side, we can see two different waves of different amplitude. We have a higher amplitude wave and a lower amplitude wave, right? It's just the height from the middle to the top, How big is that wave? We have the wavelength, and that's just the distance from crest to crest. So here's one wavelength, here's a shorter wavelength, and an even shorter wavelength, distance from crest to crest. We have a frequency of the wave, and this one's a little bit more difficult to see on a two-dimensional image, but imagine we were looking at this single spot, and then this wave was going by this spot, and we could count how many crests went by the spot in a second. So 1, 2, 3, 4 versus 1, 2, 3, 4, or 1, 2, 3, 4, 5, 6, 7. So the number of things that go past a spot in a given second, that's the frequency, right? And one of the things you can see is the longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency, right? And so overall, we can talk about the velocity of a wave, how fast it moves, is this product of wavelength times frequency. Okay. Now, with those characteristics are good for any wave, so light waves or a rock in a pond creates waves, but specific to the electromagnetic radiation, electromagnetic waves, it turns out that all light has moved at the same speed, and that speed is given the symbol c, the speed of light, which is 3.0 times 10 to the 8th meters per second. So every single type of wave shown here, it's all electromagnetic radiation, moves at the same speed. That's really important for us because, again, we can see as the wavelength gets bigger and bigger and bigger, the frequency gets smaller and smaller and smaller, or vice versa. As the frequency gets bigger and bigger and bigger, the wavelength has to get smaller and smaller and smaller, so we maintain the product of that being equal to the speed of light. That allows us to do things like calculate the wavelength of a wave of light given the frequency or vice versa. I'll show you this calculation quickly. I won't ask you to do this in our class, but we can see the speed of light is a constant. If we're given the frequency, we can calculate the wavelength. We arrange our equation. So wavelength is equal to the speed of light divided by frequency. And so we have wavelength is the speed of light divided by frequency, and we can see that the wavelength is 6.99 times 10 to the negative 7th meters, which is also 699 nanometers, right? And over here we can see the region of visible light that we can see is about from 400 nanometers to 700 nanometers. That's what we can make out with our eyes. The other little bit of light waves that we need to understand is what happens when waves interact with each other. And again, this is true of all waves, in addition to light waves. If we have two waves, if you imagine two waves coming together, so if you have these two waves that actually came together, they will add. And if they line up, and what I mean by that, if the crests of the wave line up with the troughs of the wave, what happens is the amplitude of our resultant wave is doubled. It's just the addition of this crest plus this crest to get this trough plus this trough to get this. So this is known as constructive interference, where the wave is actually amplified, right? We end up with a bigger amplitude of our wave. We could also have what we call destructive interference. And so this is a case where the amplitude of our waves are offset. So the crest of one wave is aligned with the trough of another. The trough is aligned with the crest. And if these are the same amplitude wave and they come in contact with each other, it's actually going to destroy our wave, right? So these waves will cancel each other out. And so this is known as what's known as destructive interference, right? And we could go on. If you take physics, you can understand the math behind this. But for our purposes, it's just important to know if things line up, it gets bigger. If things don't line up, it's going to cancel out. Okay. So this basic idea of constructive versus destructive interference is one of the key pieces of evidence that light is a wave. And how that works was determined by what's known as the double slit experiment, and this was done in 1803 by Thomas Young. And it's a fairly simple experiment where you take some light and you shine it against a wall, more or less, a screen. And in the screen are two very, very tiny, tiny, tiny slits. So very narrow slits so the light can go through. And what we're going to do is we're going to see what happens to the light on a screen that's over here. So what light gets through, okay? And what's interesting is if you send a wave through a double slit, the wave leaving this slit and the wave leaving this slit will start to interact with each other, right? Because those waves start to spread out and they interact. And what we end up with is an interference pattern. And what we mean by that is a series of dark, light, dark, light, dark, light. Here's a picture of this experiment, some what you would actually see. And you can see regions of light, dark, light, dark, light, dark. And then in between these lights are little regions of dark. So what's happening as these light waves go through, we have all this constructive interference where you see light, and we have all this destructive interference where you don't see any light, where the waves actually cancel each other out and you don't have any light left. So anything that's going to interact like this and form this interference pattern must be a wave. You can't do this with a particle. It has to be a wave to get this interactive pattern. So that key is light is a wave. And that's really the key takeaway. So by the end of the 19th century, people knew this. We knew light is a wave. It's part of this electromagnetic spectrum, right? And we define the different types of electromagnetic spectrum by their wavelength. We know all radiation, all light radiation moves at 3 times 10 to the 8th meters per second, the speed of light. And we know that's a constant, which is equal to the frequency times the wavelength. However, at this time, there was still some properties of light that couldn't be explained by light being a wave. And the two things we want to look at quickly are what's known as the emission of light from a glowing hot object, which is also known as black body radiation, and the photoelectric effect. So let's look at each of these in turn and then how we solved them or how it was solved. So this black body radiation, or the emission of light from a hot object, we can look at it in a couple different ways. One way of thinking about it is if you have an old light bulb that has a filament, so not our new LED light bulbs, but the old style with a filament. If you hook it up to a light switch where you can control the voltage, if you just put a tiny bit of voltage through, what happens is the filament starts to glow orange. If you apply more voltage, as in get it more energy, what happens to that light bulb is it glows white, right? So, and it also ends up being hot to the touch, right? So what we're seeing is as we apply more energy, we're getting a different color of light coming out. And this really confused people at the time when they were studying it. And the reason for that is if light is a wave, if you give it more energy, the color should not change, right? Because color has to do with wavelength. What should happen is it glows a brighter orange, right? Your amplitude should get bigger. We shouldn't be changing our wavelength, right? Which is what's happening. So this, again, really baffled people at the time. The second phenomenon people were studying is what's known as the photoelectric effect. And what this is if you have a piece of metal, so here's a piece of metal, and you shine light. So here's your light, here's your light, here's your light. If you shine your light on the metal, what takes place is you can eject an electron from that surface and actually conduct electricity. And it turns out if you do green light or purple light, you can eject that electron, right, and conduct electricity. However, if you do red light, you can't eject an electron. And the problem with this, according to the wave theory of light, is that no matter how much red light you use, you'll never get an electron ejected. And yet the tiniest bit of green light, or the tiniest bit of purple light, eject that electron. So what's actually happening? Why can't red light do it, but these other lights do it? And how this was explained was first by Max Planck, who wins the Nobel Prize in Physics in 1918. And it's in recognition of the services he rendered to the advancement of physics by his discovery of energy quanta. So what does that mean? What he says is that what if energy is quantized? And what we mean by that is, what if energy can only be absorbed or emitted in packets of energy that he called a quanta? And the change in energy of light does not have to do with a wavelength of light or the amplitude of light, I'm sorry, but instead energy comes in these little packets or balls of energy that are proportional to the frequency of light. So if we take our glowing object and we make it hotter and hotter and hotter, if we're going to release more energy, we're not changing the amplitude of that light, we're changing the frequency, right? As the frequency gets higher and higher and higher and higher, right, different wavelengths of light will be emitted. So energy is proportional to the frequency of the wave and not the amplitude of the wave, right? So that's the first sort of takeaway message. So as we give this filament more energy, we're going to get packets of light coming out that have an energy at different frequencies. And when you start getting a bunch of different frequencies of light, you end up with white light, right? So white light is all of the colors of the rainbow put together. And that's what we're seeing here. We're giving it more energy, so we have a bunch of different frequencies of light coming out. Then, a few years later, Albert Einstein comes into the mix, and he wins a Nobel Prize in 1921. And this is for his discovery of the law of the photoelectric effect. So building on Planck's work, he takes this idea of this quanta of energy. And what Einstein says is light is definitely a wave, but light is also a particle. And it's a particle called a photon. And light and the energy of a photon of light is equal to h nu. So h is just a constant. H is just Planck's constant, so this is just a number. And so it comes in these particles, again, as proportional to the frequency of light. And so the reason why red light will never eject an electron and conduct electricity is no matter how much red light you use, you're never going to have enough energy because the frequency is not high enough. Yet the instant you go to green light or purple light, the frequency is high enough, you meet the minimum threshold of energy, and we can eject that electron. The analogy I like to give here is imagine this piece of metal is a piece of glass, and red light is a ping pong ball. No matter how many ping pong balls you throw at that window, you're never going to break that piece of glass. But the green light is a bowling ball, right? So the slightest tap of one bowling ball shatters the glass, right? We've increased the energy by changing the wavelength of the light. So one of the key takeaways of this then is energy of light is absorbed or emitted in multiple quantas or photons of energy. So light is now a particle, and each particle has an energy related to h nu. Recall, we also know the speed of light is equal to the frequency times the wavelength. So we can actually rearrange this equation and put it in terms of wavelength and say the energy of light is equal to hc, both constants, divided by wavelength. And the key takeaway of this is that the energy is inversely proportional to wavelength. So as our wavelength gets longer and longer and longer, energy goes down and down and down. As the wavelength gets shorter and shorter and shorter, energy goes up. So the shorter the wavelength, the higher the energy. This allows us to calculate some things. And so if you wanted, you can go through this calculation. I'm just going to pop right to the answer, but we can calculate the energy of a photon of red light versus blue light. And if you go through it, here it is all worked out. And the only thing I'm going to point out to you here is just that notice the difference here of the energy of red light to blue light. And we can see the energy of the red light is less than the energy of the blue light, which is why if anybody ever develops their own film, if you go into a dark room, you use red light in the dark room because it's the lowest energy and won't develop your photo paper, whereas blue light will because it is a higher energy light. So we have sort of a quick recap slide now. So we now know that energy or light is a wave and it's a particle, right? It's both, and we, depending on the theory we use, depends on what we're trying to explain. So what does this have to do with the atom? Well, let's tie this back to the atom real quick as we wrap up this lecture. And another phenomenon that was known about 1800 is William Holliston was studying the spectrum of light from the sun. So he was just looking at the light that comes from the sun. And as you probably know, if you take light from the sun, send it through a slit, send it through a prism, right? And you've probably seen this many times. You send light through a prism, you get the colors of the rainbow. You're separating out the different wavelengths of light. So the different wavelengths of light deflected a different amount, and we get the rainbow that we see. But when Holliston looked at the spectrum coming from the sun a little bit closer, what he noticed was you don't actually get the full spectrum of the sun. You get most of it, but there's these discrete wavelengths of light that are almost missing, that don't show up. And again, this really confused people at the time. What's going on here? And so what it turns out is happening is if we take light from the sun, white light, you get the rainbow. But interestingly, if you take a lamp that's made of a single element, right? So for instance, hydrogen. So if you put a little hydrogen in a lamp, apply a voltage, excite it, it'll glow like a neon lamp, if you will. Send that through the prism. Instead of getting the full spectrum of light, you get discrete wavelengths of light. And each element actually gives different wavelengths of light. So you can start to see sodium gives these two yellow lines, an orange and a blue, hydrogen, purple, blue, blue, red, calcium shown here, mercury shown here. So different elements will give different line spectra. And you can actually use this to identify what elements are present, because each element will give a unique line spectra of wavelengths of light. This has been used for a couple different applications. We can use it to identify elements. If we blow crap up, it'll change the colors we want. So you can use this to one, figure out, oh, do you have lithium? Put it on a flame, glows purple, sodium glows yellow. If you shoot it into the sky and blow it up, we get fireworks, right, of different colors. And those colors come from what elements are present in the firework when it explodes. The other interesting thing about this is if we do the reverse, and so here's what we're looking at. Sodium lamp goes through, you get 2 yellow lines for sodium. If you take white light and send it through sodium before it goes through the prism, you get the full rainbow of color that you would get from white light, but now you have 2 lines that are missing. The sodium absorbed 2 wavelengths of light, and it's the same light that would be emitted by the sodium. So we see the difference between what's known as an emission spectrum, where an atom is giving off wavelengths of light, or an absorption spectrum that results with an atom absorbing wavelengths of light. And these two processes have to be related because it's the same wavelengths that are being absorbed and emitted. So going back to that spectrum of the sun, one of the interesting things is if you look at the absorption spectrum from a star, such as our sun, and you start to see missing lines of light, these wavelengths of light that are missing, these correspond to elements. And if you start marking them up, you can start to identify what elements are in the star. This is, for instance, how we know our sun is mostly hydrogen and mostly helium. And in this star, as shown here, there's definitely some sodium, right? So we can start to see what the universe is made from afar just by looking at the light that's given off. Okay, so by the end of this lecture, what I hope you have understood is light is both a particle and a wave. The energy of an electromagnetic wave is proportional to the frequency of light. And atoms will give off a unique line spectra consisting of specific wavelengths of light. And this allows us to determine what elements are present. What we're going to do next is start to apply these lessons of light to the atom and to the electron as we continue to build our model of the atom. Thank you.